material today begins with finishing the last lecture, which had to do with the made-up exercise that you are to discover on your own how to connect by flow a point situated at a distance L from another point. This is a very simple problem because almost everything that you see in nature, but also in engineering, does not flow from one point to a point. It flows from a source to a population of users. I'm talking about nature in general, and the so-called users, where sinks are covering an area. So the flow is from one to very many, or in the other direction, from very many to one. The other words for this duality, represented by the same drawing, incidentally, is spreading and collecting. Both can be very good, and both could be very bad. But the drawing is one, just like the architecture of the human lung. One drawing, but the direction of the flow could be both outward or inward. So what you learn, one thing you should keep in mind is that the challenge of predicting design in nature or outlook is not about the direction of the flow. It is about the birth of the image, that image that should first happens in your mind. So don't play around with your mind, by the way. Your mind is very, 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 very important. All right. So that's the, that's funny. M dot here. And we went through a make-believe story of, let's call it incompetence, beginning with a whole bunch of things, drawings, including braided flow. Incidentally, braided rivers happen only on almost horizontal surfaces, and that's the hint that the braided river has to do not only with a river but also with a delta. And then on an incline, some other configurations pop up in your mind. And the one that won that competition for respectability in my mind turned out to be the straight duct. Let's draw here a equilateral triangle for the cross section. A straight duct. So straight. And the cross section should be a regular polygon. I'm not sure you're wondering what this word means in Greek. Poly.
I think I know what it means.
Tell us.
Many sides.
No. Many, yes, but
Many, what is gone?
Gon means comes from corner, angle. From which the most difficult task in geometry, because all of you are studying geometry, is to find and then hide in the corner of a perfectly round room. There's a name for that, which is called infinity of corners. Okay, we'll get to that in a second. By the way, this is not a good length for the stick. And we for this champion of all champions, still undetermined, because the number of sides of the polygonal perimeter is not specified. This is the drawing with n equals 3, where n is the number of those sides you're mentioning. So the punchline, it's not a punchline, but people think that the punchline could only be expressed mathematically. Well, the punchline is also even better expressed as a punchline, as a short statement. That statement is that the pressure drop responsible for pushing the stream through the tiny opening, because you see, nothing moves unless it is pushed. That's that's another way of talking about nature. And by the way, and the pushing comes from power. I think I told you. And the power comes from flow architectures, that is, designs that function as engines. If you run into people who poo-poo your decision to study mechanical engineering, tell them nothing moves unless it is pushed. The pushing comes from power, which is spent, and the power comes from engines. An engine is the subject or the object of mechanical engineering. This discipline of yours did not exist before the originally called fire engine, meaning the engine driven by fire. Later it became known as the steam engine because the locomotive was, exhaling thing that looked like cotton, the cloud of, never mind, the steam engine. So you're soon becoming disciples of an indispensable part of knowledge called mechanical engineering. All right, so this thing, which expresses the how much pushing you have to provide by employing the big pump, or if it's a compressible substance, a compressor, turns out to be mu. This is the kinematic viscosity, also known as mu divided by rho, times the length of the duct to power 3, and then 8v squared. This is the flow volume. And then a group written as a Poisson number times wetted perimeter to power 2 divided by the cross-sectional area. Now, several things you should write down. There's a typographical error in the textbook. This exponent 3 is missing in equation 3.1 in the DCT book. The thing to note is that this group depends on the shape of the cross-section. This group is drawing dependent. So shape, it has one value for the equilateral triangle, another for the square, and so on and so on. This brings us to the real punchline, which has to do with how these polygonal shapes perform relative to each other. Which one is the better than its neighbor? And this discussion in the textbook is displayed in two ways. In fact, I don't need my notes for this. One of them being tabular. So this is table 3.1. It has several columns. One of them is the group shown here. I'll label it with a box. this box is called very soon a dimensionless. That's dimensionless, you see. Length squared divided by area. The Poisson number is a constant. I'll list that very soon. Okay, so this f with a hat is a value for each regular polygon. Let me put here the number of sides of the polygon, for example, 4 and 6 for square and a regular hexagon. And the value of this measure of imperfection, because you have to spend power in order to have a flow, turns out to be 227.6. Sorry, that's for 4. And 208.6 for the regular hexagon. In this direction of increasing number of sides, of course, you can place yourself in the corner of the round room, and that is a regular polygon with an infinite number of sides. In which case, that is in the limit, the number on the left-hand side is 201.1. And so, in this column, you have the shape. If you want to, and over on the left-hand side is the degree of imperfection. If you want to think of it in relative terms, then you can divide all these numbers by the smallest to obtain here, in other words, you divide the f with a hat by the f with a hat for the round tube, and get here 1, and then 1.037, and then 1.132. I hope you see, this is, I don't know, for the upteenth time, that perfection is doesn't require saluting very much, because other tubes with flat sides perform nearly as well. And in other words, you'll see very soon graphically in figure 3.2 that if you plot these results with this number f hat on the abscissa, and on the ordinate you plot 1 over n. In other words, that would be 0, 0. You can make the graph, and obviously the smallest f values for n equals infinity, and then the other ones for other values of n align themselves. They actually they do not describe a continuous line, because the values of n do not change continuously. These are integers, all right? So the reality of constructing ducts is a progress toward this is perfection. Populated by many, called diversity. Yes.
I understand how there's no need to be perfect, but I feel like I've seen a lot more square like air ducts than hexagonal air ducts? And for like a 10% better performance, would it not be worth making ducts hexagonal instead of rectangular?
Yeah, this is a very good observation, and I'm glad that you're telling everybody to go through life with the eyes open. Yes, this is the reason why you see these square ducts. But now that you brought up the real world, there are other reasons to use square ducts and hexagonal. And they have to do with the fact that in other boxes, they look like boxes from the outside, but you don't know what's inside. These are heat exchangers. Try to imagine, okay, so I'm now deviating from what I was reciting to myself during the night. Heat exchangers, the best heat exchanger when it comes to avoiding imperfection is the counterflow heat exchanger. That is the proposition of mating thermally two streams, a warm one with a cold one, so that all along, meaning inside the box, the warm is heating up the cold. So here's the box. And the box is three-dimensional. It has a frontal area, let's say this one. You see? And this stream does not flow through one duct. That would be not very intelligent, because a single duct doesn't have a big enough perimeter. These heat transfer arrows have to pierce the surface of the duct, which is the size of that is proportional to the perimeter of the duct. So the cross-sectional area here will be drawn this way, square, or some other thing that looks like a suitcase, must be packed with the capital A's. Where is the capital A? This one, of each duct. And yes, you can pack, now to answer your question, you can pack this big box with ducts of square cross-section. In this corner, I'll sketch the packing. In fact, let me show more than, okay. And through this maze, it's not a maze, it's actually parallel ducts proceeding away from you into the blackboard. Some of them, through some of them, the flow is into the blackboard. Those in counterflow will be flowing toward you. You see that? And let's see whether this packing really works toward the larger boxes. Well, let's see now. It does work. In other words, you have as many dots as you have crosses. Where have you seen this convention of leaving and coming? This means coming toward you. This one is leaving. Where have you seen it?
Physics.
You, because you spoke.
Currents.
What?
Like when you're talking about currents.
Like in electrical engineering, okay?
Is it in chemistry with chirality of molecules?
Really? I don't know the answer to my question, except that when I was a kid, I was playing with bow and arrow. So this is what you see when you launch the arrow. This other one, I never saw it because I was never hit by an arrow. But yeah, but that's the origin of let's call it symbolism, which shows you once again that communicating, in this case, technical information or scientific jargon, is in fact storytelling. and that activity employs images from the distant past. And these images are both graphic and also part of the language. So do not run away from the other things that people taught you. Oh yeah, what about the hexagon? Well, you can pack hexagons. You see this in the this thing that the bees make out of wax. It's called a honeycomb. Honeycomb, right? But packing hexagonal ducts in a volume in such a way that the number of channels that leave equals the number of channels that approach, that's a more challenging proposition. So if you want to play with that mental game, yeah, contemplate it, and you may even make it your own term paper, but it's probably, you shouldn't do that, because the term paper should come from your own imagination. All right, so coming back to this drawing, we have, as I said, perfection and diversity coming together. Perfection, incidentally, is an exaggeration when it comes to round pipes. Every single pipe has that's manufactured has a particular degree of wall roughness. The so-called perfectly smooth pipe wall, well, maybe there should be the Olympics of smoothness for people to break the record from 4 years to 4 years. Everything that a machine does or a polisher does is, well, by definition, personal, therefore imperfect. Or if you don't like that part of reality, then if you hear people talk about nature designs perfection, as, for example, biologists will tell us the round cross-section of the blood vessel. Yeah, think about it. Your body is bending all the time, and all the so-called circular cross-sections are fluctuating according to the rhythm displayed by the moving animal. Even more obvious is the fact that the boxer in the ring gets hit in the abdomen or someplace, or the chest. All the tubes there become slightly so depart from the round cross section, but the fighter remains. You see, and the persistence of the flow system, in this case the animal, is due to the fact that the almost perfect, meaning the diversity of shapes, performs essentially the same way as the perfect. Another piece of jargon you may have heard is called design space, such as this territory here that accounts for very many drawings, these cross-sectional shapes and other shapes that are not regular polygons. So I'm glad I stumbled upon something I was going to miss. If this is the square, meaning 1/4, meaning n equals 4, then to the right of it are all the quadrilateral cross-sections that are not square. For example, this one, or this one, or this one, and so on. So the pink frontier, which is again not a continuous line, separates the world of the mortal designs. Those are the so-called domain of the possible, from the rest of the design space, which is the impossible. And to know that the so-called freedom to explore drawings is divided into a smaller space, which is accessible, and then a bigger one that is forget it, meaning not accessible, like violating violating the ideal efficiency of Cardinal. This is a very important conclusion to store in your very few mental notes.